Great. Our next talk will be Sam Westrick, Automatic Parallelism Management.
Great, thank you so much. So thank you to the organizers for the invitation to speak. When I got the invitation, I saw this was a managing parallelism workshop, and I thought, well, that's perfect, because I have the perfect talk to give, because we have this paper, automatic. Say again?
There's a typo in science.
No, there is? Oh, no. Sorry.
Apostrophe.
Oh my gosh, okay. My fault. Okay, I will fix. Okay, thank you. But we have this paper recently that literally with the title Automatic Parallelism Management. So I'd like to tell you a little bit about this work. I'm really excited about it. This is kind of more of a PL, compilers, runtime systems talk, just to kind of set the stage. And to set the stage a bit more, this is really in the context of a research compiler that me and many of my colleagues have been developing over the past 10 years or so. So this is a compiler that we call Maple, or MPL for short. You can find it on GitHub, you can download it. It should install fine on both x86 and on Macs. Like the newer Macs, it runs on ARM as well. Lots of people involved in this project. So my advisor back at CMU, when I was still a PhD student, that's Westrick, but we also worked closely with Guy Blelek on this. And Matthew Fluitt at Rochester has done a ton of compiler work and has taught us a lot about compilers specifically for this project. So this is a kind of safe, mostly functional programming language. Okay, it's in the ML family of languages, not that ML, but the other ML. It stands for meta language. Anyway, it goes back to a family of languages developed back in the 70s for implementation of theorem provers. But nowadays we've found kind of more and more applications of these languages. And there's an undergraduate course at Carnegie Mellon that teaches parallel algorithms designed by Guy Blelek and Westrick, and they ended up choosing ML as an implementation language to force students to think carefully about their algorithms, but also at the same time to avoid issues with data races, race conditions, and these sorts of problems, which generally kind of completely distract from the question of thinking about parallel algorithms, right? So we had this course at Carnegie Mellon, but it was not actually parallel. We just had a sequential implementation of this ML language. And then my PhD work basically turned into creating an actually parallel compiler to run some of these codes. So there's this whole theory on efficient parallel memory management. We have a parallel garbage collector, which is provably efficient, using a cool new strategy called disentanglement. That is not what I'm going to talk about today. I'm going to talk about something else today. So I'll just mention this is used by hundreds of students at both CMU, and now I'm using it at NYU. I just started at NYU a year ago. I'm using it at NYU now to teach parallel algorithms. One of the really nice things that we're able to get is a fairly competitive performance against C++, actually, with this compiler. And let me just kind of briefly describe what precisely do I mean. So we have this benchmark suite. We took a bunch of existing code, say from PPBS, but also related libraries and projects, Parallelib, GBBS, Ligra, PAM, some of these libraries, and ported all of these to our system. In doing this, you run immediately into an interesting challenge, like what does it even mean to port these into a different language? Okay, but what we found is that it's reasonably possible. Okay, so if you see like an array of structs in C, there's kind of a natural translation into sort of like a sequence of tuples in our language, and we have all of the same common primitives that you might be interested in using: parallel prefix sums or scan, parallel reductions, filters, compactions, all of these sorts of things. Okay, and in general, we are able to, for the most part, ensure the same memory representation and access patterns as the original benchmarks that these were inspired by. Yes?
So what about, is there any imperative component? Like those implementations sometimes would use atomic variables and like those tricks. Is this where the diverse, or do you also have a way of?
Yeah, absolutely. So this is where some of the artistry in this comes in. So absolutely we allow for mutation and imperative computation, but we try to minimize it as much as possible. And actually, if you look at PPBS, what you'll find is that a surprising amount of the code is actually like somewhat functional anyway. You have maps and reductions and parallel scans, and all of these things can be encoded essentially with a purely functional interface. Some data comes in, some data comes out. And we can do the same in our system. But yeah, we fall back on mutation whenever we have to. Here's a very rough summary of just like right now, what do we have? So if I run this on 72 cores, I can get up to 40x speed up over sequential C++ implementations. And then if I compare parallel versus parallel, we're kind of in the ballpark of 1 to 2x, okay? And my active research right now is on closing that performance gap. There are many computations actually where we can match the performance of C and C++. Oftentimes those are things like memory-bound computations where you're bottlenecked by the throughput, by the memory bus anyway, and if we're matching the same memory representation and access pattern as the C++ code, then we're getting essentially the same performance, okay? But there's other things that, like basically the active area of research here is getting a little bit more control over particular compiler optimizations, and my kind of hot claim or hot take is that I think in the next 5 or 10 years we'll be able to completely close this gap. I actually don't think there's anything kind of fundamental preventing these high-level languages from competing. Oh, yeah, yeah, go ahead.
So maybe you're going to talk about this, but like, how much does the programmer have to think about parallelism, or have to think about how many processors they're using, or anything like that?
Yeah, so they have to think about parallelism in exactly the same way that you have to think about it in Silk or in Parallelib. You're thinking about explicit parallelization. You're thinking about parallel for loops, binary forking, synchronization overheads, all of this. So you have to think about the parallelism very explicitly. And then when it comes to the performance optimization, you have to think about the memory layout very carefully. But I think that's kind of a shared concern in most of these systems. Those are the two things that you're kind of like zeroed in on. And I think the remaining gap is getting control over these kind of compiler optimizations that are making the difference between getting exactly the right access pattern or not, for example. You have a question too?
Did you use any LLMs for converting this code?
No. So I did this conversion code myself, and as well as with collaborators, as much as 10 years ago now. If we tried it again, it would be interesting. Maybe it would, maybe do really well. Okay, so that's just to kind of give you the lay of the land of this compiler that we're working with. But now I kind of want to change gears and talk about this automatic parallelism management, which is a new feature we've added to this compiler recently, taking advantage of the fact that we have full control over the compiler. We have full control over all sorts of things, and we can do things in this compiler that are not easy to do in other languages. Okay. So what I want to talk to you about is the granularity control problem. I'm sure everybody is probably deeply familiar. Here is some real code you could write in our system. This is a parallel traversal over a tree data structure. So you can see there's two cases. Either you're at the leaf of a tree or you're at the node of a tree. And what we've done here is we take a function as argument. It's called func. And so this is higher order traversal. I can now take that function and I can apply it to any element at the leaf. Okay? So you get down to a leaf and you apply the function. Right? This is a fully parallelized traversal, and if anybody's written, Silk, Parallelib, OpenMP, you're probably immediately thinking like, oh my gosh, there's no granularity control here. How can this possibly perform well, right? Because typically what you would try to do in practice is switch to a sequential traversal at small sizes. And there's all sorts of kind of problems with this, by the way. I mean, like already I need to augment my tree with size information in order to be able to do that granularity control strategy. There's like already problems with this approach, but this is probably what you would try to do, some sort of size-based granularity control, or perhaps a depth-based granularity control. Okay, so after getting below depth 10, maybe you switch to sequential, something like this. But even that, what if you don't know the structure of the tree? So arbitrarily structured tree, perhaps irregular. It could be not too deep. Maybe it's still logarithmically depth, but you don't actually know exactly how deep you need to go before the parallelism really starts to matter, for example, right? And you can easily cook up, examples where you can get, say, a 10x or more gap in performance between these two implementations, right? But there's something kind of like fundamentally problematic about this granularity control strategy. You have to change your data structure in order to even support it. And it's not fully general. It can't handle all cases. So you might hope that this is what an implementation would be good enough, right? But now imagine you're a library designer. You want to provide a tree data structure to your clients. And one of the things you'd like to provide as a method on that data structure is something like a higher order traversal. It's a very reasonable kind of library function that you would hope to provide. But what grain size should you choose? Maybe you just punt it off to the programmer. So you make it part of the library interface, and you make it the programmer's problem. Okay? That maybe can solve the issue. But here's 3 different cases. You can imagine in one case, you might be traversing a tiny tree with a very expensive function that you want to apply to each element. This is a case where you essentially don't want any granularity control at all. You want maximum parallelization across the entire tree. But in a different case, you might have a massive tree, maybe on 1 billion nodes or something, and a very cheap function that you want to apply to each one of the leaves. That's a case where you want a very large grain size. That's also a case where potentially this granularity control strategy just won't work at all if the tree is very irregular, where the structure of the tree, well, I say don't work at all. It might work reasonably well, but it's not going to be optimal or anything, right? Where if you have some very irregular tree, perhaps with like a long chain at the top and then it gets big, something like this, something strange, right? Or the other case where to make this perform badly is you have a lot of like kind of singleton nodes hanging off in strange places, right? And so all of those singleton nodes are still going to be affected by the spawning strategy and incur all the spawning overhead. Okay? You might even do something like, I don't know, do nested parallelism once you get to a leaf, right? So things get very complicated here. So we want an automatic strategy to kind of completely eliminate needing to worry about this granularity control problem, and that's what we've been working on. This is what we call automatic parallelism management, is this idea of taking the amount of parallelism in the programming, in the program, and automatically managing that. So that's what we mean by. Or you could think about it as automatically managing the overheads of the parallelism itself. And that's really like spawning tasks is the overhead. Okay? Sorry, if I didn't mention already, I'm really targeting like CPU, multi-core kind of style parallelism, and the overhead of parallelism that we're thinking about here is the overhead of spawning a task. And in our particular language, that looks like this par construct. Par says do two things in parallel. But you can imagine this is also more general. Parallel for loops, you know, any sort of parallel construct has to spawn tasks in some point, and we want to automatically manage that spawning. So surely this could be automated, and there's tons of existing techniques to automate it. Okay, here's a few papers that we're kind of taking inspiration from. This is very closely related to. There's kind of another line of work, which is this idea of towards getting zero spawn overhead. There's a paper actually from the most recent SPA that's exactly on this topic in Silk, and so this is very closely related to those works. The thing that we really want is a fully general solution that's provably efficient in all cases. So that's the thing that we're using a particular technique that we call heartbeat scheduling. This is an idea that comes from also at the same moment installing the possibility of executing something else in parallel. Okay? So here's what it looks like. Here's a standard call on the left, as we're all familiar with. Stack grows down, of course. And you push your return address, you push some args, and then you have a new frame for the next call that you're executing. Something I'd like to imagine here, we're doing a two-way par. So what we're going to do is we're going to do a function call on one side, and then we're trying to install some potential parallelism for the other side. Okay? And that's what we're going to be doing with pcall. So conceptually, you can think about pcall as using 3 return addresses instead of 1. The 2 additional return addresses are an interesting mechanism for enabling that potential parallelism. But the idea is, let's even just think about the sequential case. The sequential case is going to be identical to the regular call. You have a normal sequential continuation installed with a normal return address. Okay? And if you get back to that return address, you just go to the other side of the par and you keep running it. Okay? So that's the sequential case that is nearly zero overhead. We have these 2 additional return addresses. I'm visualizing them here as actually being pushed as additional arguments on the call stack, but actually you can store them separately in a static lookup table generated at compile time, and that's actually what we do. So they're not even in the call stack. They're just in a static lookup table that's associated with ret-seek. Ret-seek is essentially an index into a lookup table that you can then find ret-sync and ret-spawn. So what do ret-sync and ret-spawn do?
So the index is stack relative or something? I mean,
No, think about ret-seek as like literally like it's just a sequence of bits. It's a return address. And I'm using that as a key into a lookup table. It's a little bit sillier than that, but that's the basic idea.
but you could have multiple instances of it, right? Just like I have, like this return address is, I could, if I have recursion, I can push the same return address on the stack.
Yeah, but you're getting back to the same code position. Like it's statically, these are 2 different code positions that are statically associated with that code position. So if I'm getting back to the same position in my control flow graph, I have statically associated with that position in the control flow graph 2 alternative code paths that are also statically known at compile time. Everything else is dynamic data, but these aspects are static. So here's how we use the 2 additional return addresses in order to implement a promotion. We are going to redirect this return address to do something different. And we call this ret sync because essentially what you're doing is you're installing synchronization code rather than the default sequential continuation. So rather than going back and continuing the program sequentially, when this function call returns, it'll instead switch to some synchronization code that waits for the other task. The other return address is a hack to generate a new task. The way that we generate a new task is by literally copying the frame. We initialize a new call stack from that frame. We give it this ret spawn return address, and then we simulate a return into this call stack. And that essentially, it's as though you returned from this function call, but without a return value, and took some other strange code path. And we can use that other code path in order to implement the other side of the par. So that's the actual mechanism for doing promotion. And that's a constant time action because your call stack frames are constant sized, okay? But it's a modest cost. And once you spawn the task, then you have to push it into a scheduler queue. Maybe you have to release it into a work stealing scheduler or something like this. So that's where all of the overheads are happening. But it's only happening at promotion. Okay. Now we get to actually schedule these promotions. Okay. So the idea that we're using here is an idea that we take from this paper called heartbeat scheduling. Okay. We've adapted this idea slightly to make it more implementable in practice, and I'll come back to that in a second. But here's our algorithm, okay? The idea is you have a regular pulse in the system every n microseconds, right? It's a fairly fast pulse, okay? That's the heartbeat of the system. And at every heartbeat, I am going to just give tokens to all of my active threads. Those tokens are explicit amortization tokens. Anybody can spend a token at any moment to perform a promotion. Okay? So this immediately gives you an explicit amortization strategy for the number of spawns that will happen. Okay. I can bound the number of spawns by c divided by n, right? Just that's how many tokens I get every n microseconds. There's a really interesting detail, which is that we have to pick a particular frame to promote in order to guarantee that the critical path doesn't get screwed up. You have to pick the oldest one. And some intuition for this is that that's the one that has already been delayed the longest. So it was like logically spawned in the past, but it has not yet been released to be actually executed. It's the one that has been delayed the longest so far, and therefore it needs to be released as soon as possible. So I need to get back, I need to jump very far back into my call stack to find the oldest, most promotable frame. And in order to do this, this is one of the places we deviate slightly from this idea of nearly zero cost, okay, or zero cost. We need an auxiliary data structure in order to get constant time access to the oldest promotable frame. And we call it a promotion stack, but I mean, it's related to the concept of a display, if somebody has seen a display before. We have to execute like 1 or 2 instructions on a function call, on a P call. So at a P call, what you do is you push your current frame pointer onto this promotion stack in order to keep track of the fact that this frame is promotable. Because you can intermix promotable frames with non-promotable frames. I can write arbitrary code. I can do a P call at any moment. And I might be deep in the call stack, and I might be nearby non-promotable frames. So I have to keep track of where they are. Okay? And that I can actually do all of this promotion stack manipulation statically in the generated code. Every time I return from, every time I do a standard return from a P call, I can fix the bottom up. And every time I do a synchronization return, I can fix the bottom and the top up. And promotion moves the top. So it's kind of like a little deck, right? So now I can say something about work and span efficiency. So just a reminder, this is the algorithm that we're using. Every n microseconds, that's the heartbeat rate. We get C tokens, and at any moment somebody can spend 1 token to promote. And I mean, actually what you want to do is you want to spend your tokens as soon as possible, okay? But you're allowed to save tokens in our strategy. So if you have leftover tokens, you can hold on to them. And as soon as you have an opportunity to spend them, you can, okay? The reason why we use this strategy with tokens is because I actually don't really have much control over n. N is the heartbeat rate. If you look at the original heartbeat scheduling work, they do some analysis and figure out that on modern hardware, a good choice for n, which is something, by the way, you only need to tune once for a machine. It's not per benchmark. You tune it once for the machine, and you never have to touch it again. Okay? they figured out that an optimal choice for n on modern machines is probably something in the microsecond, or like low microsecond range, 5 microseconds, 10 microseconds. If you try to ask a Linux to deliver you a signal every 5 microseconds, good luck. I mean, I think the best I've gotten is maybe every 100 microseconds or so. Maybe every 200 microseconds is a bit more consistent. Okay? And if you just take naive heartbeat scheduling is going to be the case where essentially you only get 1 token on every heartbeat and you're not allowed to save it. It doesn't perform well. The delays along the critical path are too high. Okay? So what we did is we said, okay, well, I can only receive a heartbeat signal, let's say once every 500 microseconds. Let's be conservative. Well, now I can just tune the number of tokens I get to make sure that I have tokens to spawn essentially effectively at the same rate that a faster heartbeat would be capable of. Okay? So the work analysis is very straightforward. So you can imagine the sequential program, like the sequential elision, the program that has no parallelism in it, has some sort of ideal work, W. And with this strategy, we incur additional costs due to spawning, and we're going to call that tau. And the number of them is going to be at most like c divided by n. So you get this kind of plus c divided tau times c divided by n in your work term. So it's a provably efficient. We're saying you can tune c and n in order to guarantee that the work overhead due to spawning is provably small. And you can just like tune these to be guaranteed less than 1% or less than 5% or whatever you'd like.
I'm missing something basic. Why is the number of threads not coming into this?
It's a localized strategy for spawning. So actually, it's completely independent. You don't care how many threads are in the system. Each thread is operating, each scheduler thread, let's say, is operating locally on a call stack. It receives a heartbeat signal. It does a spawn. It doesn't care about the rest of the system.
So every unit of sequential work, there's some thread that's executing that, and they execute that plus this fraction of overhead.
Every spawn is amortized against true work that the program has already done.
So
yes.
are you were always working on the oldest frame, or it's not always, but that might be the critical path, but it might not, right?
Yes, yes. That's interesting. The insight from heartbeat scheduling. There's a full proof in heartbeat scheduling, actually, the heartbeat scheduling paper. You can find it's a PLDI paper. They actually did if I remember correctly, a mechanized proof of this. It's like a very rock solid proof where they proved that somehow blindly choosing the oldest frame guarantees constant stretch of the critical path in the worst case. I have a slide in a moment to kind of visualize that. Maybe it'll be helpful, but. So just like a very naive analysis for the token-based strategy, Heartbeat already has this nice proof, you can find it in the paper, of the constant stretch, and they prove this for heartbeat scheduling. And then our system basically is some constant on top of this. We have a bag of tokens. It's kind of like a bag of promotions rather than just one. So it's some constant factor essentially times the heartbeat bound is some intuition. That's a very loose kind of bound. Frankly, I would like to do a more precise analysis of the token-based strategy because it seems to work pretty well. Here's some intuition for the heartbeat schedule. You're moving these spawns a little bit later, and you're delaying by some interval, and you're using that to amortize the cost of the spawn. You can get these delays accumulating along the critical path, but the worst case is that you're stretching by a constant factor. Intuitively, you can kind of see it visually here. I mean, every time I do a spawn, I might have been delayed by some constant length, and that can accumulate along the critical path, but that's a multiplicative factor along the critical path of some constant. That's like approximately the intuition for this proof. The actual proof is quite intricate, actually. And involves like a fancy amortized or a potential function analysis. And, good. So we've implemented this. We can run it. Yeah.
The fact that I can hold unspent tokens, obviously is not going to change the analysis, right? That's just a performance optimization.
That's right. And actually, we do a few optimizations on this. So we put a max on the bag of tokens. You can't arbitrarily accumulate tokens. Okay. The reason for that is that otherwise you can get this kind of like non-local performance problem where I run a long sequential computation, I accumulate a massive number of tokens, and now I run a parallel computation, and the performance is terrible because you just spawn everything. So we localize it and we say, okay, you can only hold at most 100 tokens. You can't hold more than that, And so we bounds that kind of like non-local effect. really, I like to think about the tokens as only just mitigating the difference between one interval with many promotions and a tiny interval that's equivalent to, like, I don't know, n by c.
But if you're spending your tokens greedily, like as fast as you can,
Yeah.
then the only case you're not spending them is if you don't actually have C things that are.
Yeah, the only possibility for saving
You're not
tokens is
seeing
there's no
people's-
parallelism in your to promote. That's right. Yeah. So actually, one nice feature of that is that as soon as I get to the next P call, I immediately promote it. So there's actually no delay in that case. Just some quick experiments to show you. So old maple, new maple. So the new maple has this P call strategy. And what I'm showing here are overheads relative to manual tuning. So I can manually tune granularity control in all of these benchmarks, right? That'll be the 1.0 line. And everything else is a ratio relative to that. So the blue line is if I just don't do any granularity control whatsoever, and I do the traditional eager spawn for a par. Okay, a huge overhead. I mean, I mentioned 10x earlier. You can easily contrive examples to get like 50x. Okay, and then with the new strategy, it's much lower, but it's not perfect yet. I mean, there's like a few cases where it's still like 2x overhead, 3x overhead, and that's the kind of next work that we're doing to take this even further. Okay, so the problem really in these cases, I know I'm kind of like getting close to time, but I'll be quick, I promise. In most of these cases, it's usually just parallel loops and reductions that are the source of that additional overhead, okay? Here's code for implementing a parallel reduction, okay? G is some associative function, F is like a loop body, essentially. But F is generating elements, and then G is maybe addition or max or something to combine those results, okay? And this is maybe what you would implement, the fully parallel solution with our nearly zero cost par. It seems like a good implementation, right? But the problem is it's not, okay? Because there are overheads here that in comparison to a sequential loop, a tight sequential loop, are completely just overhead, and it has nothing to do with par. Even if par is zero cost, this is an algorithmic overhead relative to a sequential loop, okay? Like you can compare this against what the sequential loop would do. The sequential loop does not have to compute midpoints. It does not have to do any frame pushes and pops, okay? So that's the overhead, okay? And by the way, there's like kind of an emerging area of research on this idea of zero overhead parallelism. Here's a cool paper on an attempt at doing zero overhead parallel scans. Okay, so this is not my work. This is other people's work, but this is kind of an exciting new emerging area of this idea that the programmer just writes parallel code, doesn't worry about the overheads of the parallelism itself, and the system automatically guarantees that the overheads are small. That's kind of the vision, the research vision. So the active area of research that we have right now is doing automatic parallelism management for loops and reductions. And the kind of very high level idea is that we want to actually execute the sequential loop up until a heartbeat, and then we want to dynamically split the loop just at the moment of the heartbeat. So we're not only amortizing the cost of spawning the task, we're also amortizing the cost of computing the midpoints and doing the splitting in some sense. This is a work in progress, but the results are looking really, really good. This is my last slide, so I'm done. So this is, again, the same experiments. So the blue line, again, is the no granularity control using the old strategy that's just not going to perform well at all. The red line is that halfway point where we have par. I can automatically manage two-way parallelism, but that's it. I can only manage two-way parallelism, and I get all the overheads of algorithmic overheads between a parallel loop and a sequential loop, okay? And the new results is we have a technique that automatically manages the cost of splitting loops as well. And with this, we can get very close to manually tuned in many cases. There's a few places still where it's not, so this line fit benchmark is still maybe 2x. The word count benchmark is still approximately 2x. We've been individually poking and prodding at each one of these, and we've basically figured out that the remaining issues are only issues of loop unrolling. And we actively have a project to solve the loop unrolling problem, and then I think you're going to see it 1.0 across the board. Okay, that's it. So I'll leave you with this slide, yeah, thank you so much. Yeah.
Just curious, is loop unrolling the issue with big imagine
And Delani, why your new strategy for loops?
Oh, no, okay, wait, that's a great point. Yeah, thank you for pointing out Delani in particular. Okay, Big Not Mad is a little bit of a fluke. What happens with the red line, you see red line somehow got better than manual tuning. That was a compilation error in the manual tuning. So the manually tuned implementation actually did not compile to the optimal code. So again, this is a case where we need more control over loop optimizations in this compiler. I think in general, just having fine-grained control over loop optimizations is critical. No, but Delani is an interesting case. Delani is the case where the overheads on the critical path are actually a problem. At least that's currently my theory. We've looked into it a little bit. Delani has relatively high span. The benchmark has relatively high span. It's essentially an iterative loop of many small parallel for loops. And each smaller parallel for loop is now incurring some sort of critical path delay. I think those are stacking up. So these results, by the way, are on like 80 cores. We're looking at the overhead relative to the manually tuned implementation on a fully parallel run. And so we're seeing that cost here, and I'll go and look back at our results in the paper, but I'm pretty sure the overheads on one core are much smaller. So it's actually indicating that there might be a scalability problem. That's going to be a much harder problem to solve. Much harder. Yeah.
So all, including the manual tune, are all using just binary forking?
All of the red lines here are binary forking only, where if I want to implement a parallel loop, I do the naive thing of I just keep splitting it with binary forking. Now the yellow lines are this new strategy that I didn't really have time to talk about. It's not even published yet, so we're still working on it. But it's this idea of also taking the costs of splitting loops and also delaying those costs and moving those costs to the heartbeats as well.
But you're not trying to, like if you have a parallel for loop, you still have to build this tree of.
Yeah, that tree emerges dynamically only due to the heartbeats, though. So you get a flat execution, flat sequential execution up until the point I'm actually able to do a promotion. And at that point, I start generating the tree. We're actually taking advantage of the call stack still here. So we have actually a dynamic, recursive implementation of a loop, but you only start becoming recursive at the moment you can do a promotion. And it's a flat, tight loop otherwise.
But if I could fork N-way or P-way in a single heartbeat.
Yeah, that'd be if we could do a multi-way promotion. Yeah, perhaps that could help solve some of these scalability issues. Perhaps. In general, we really haven't seen major scalability issues. I mean, Delani maybe is the only example. I think everything else is scaling really well. I mean, that's probably just due to low span, right? I mean, most of these benchmarks are linear work and log span, so. Yeah.
I think what you're doing is by keeping probably the other thread in your current call stack, you are preventing it from moving to the scheduler, as well as preventing it by being stealed by others. So you're kind of preventing two things. But I'm curious, like, which part is the dominating part, or they are kind of having the same cost? I mean, moving things from the call stack to the scheduler, and that's the first part. The second part is a task actually being stealed by some other people.
Yeah.
So which is more expensive, or almost the same?
Yeah, that's a good question. I mean, I off the top of my head, I don't know of I don't have concrete numbers to say which one is more expensive. One way of thinking about this problem is a question of data representation. So in order to even make something stealable, you have to change the way it's written, change the way it's encoded into the bits. So we have this encoding scheme that's based on implicit representation based on a call stack. So it's essentially a zero-cost representation, right? But as soon as I want to make something stealable, I actually need to realize it into actual bits. And that's one of the costs that you incur. The other cost you incur is pushing onto a scheduler queue. Okay? And then the last cost you incur is the migration cost, which is probably a lot of cache misses and stuff. I don't know. That's probably So I think decomposing all those costs into understanding each one of them individually would be helpful. I mean, actually, I would recommend talking to TB about some of this because I think he probably has better insight. I mean, they were working on this recently, this work stealing without DEX implementation, right? Where you steal directly out of somebody's call stack, which is actually kind of an old idea, but like actually implementing it is incredibly challenging. So. Yeah, anyway.
Any other questions? Great. Continue at 2:00.